Hello everyone, this is Mingyu from University of Hong Kong. Today I will be presenting our work on dynamic visual reasoning. This work is done jointly with collaborators from MIT and IBM. Here we show a video in Clever. Humans can easily use their common sense of intuitive physics to understand what has happened, predict what will happen next, and infer what would happen in counterfactual situations. However, it is very challenging for a machine to answer these questions. Previous solutions can be divided into two streams. The first stream is pure network-based end-to-end models. They typically leverage end-to-end neural networks with powerful attention modules to extract features from both video frames and question words to get the answer directly. However, these models are non-transparent and they do not model the object's dynamics. The second stream builds graph neural networks to predict the object dynamics by treating objects as nodes in a graph. With the predicted dynamics, they perform neurosymbolic execution to answer the questions. Although these works are of good transparency, their dynamic prediction is heavily based on the graph neural networks, which is not reliable, especially in long-range dynamics prediction. The graph neural network does not consider physical laws or concepts encoded in the question-answer pair, making its prediction have errors, and the errors gradually expand over time. As a result, both previous works do not model physics explicitly, and show limitations in counterfactual situations and long-term predictions. In this work, we explore using explicit physics model to predict the dynamics of objects. If we have a physics engine to model the dynamics explicitly, the challenge becomes how to learn the physical parameters from raw video observations. Typically, it requires accurate visual perception and object concepts to build the physics model. Now let's see, how do we learn the physical parameters from raw video observations with differentiable physics engine in a neurosymbolic framework? In this framework, we have object properties and concepts as supervision. Then, given a raw video with multiple frames, we first use an object detector to parse each object into trajectories and get their properties, such as color and shape. With those object trajectories and visual properties as input, the physics model then performs differentiable simulation to learn all physical parameters of the scene by comparing the simulated trajectories with the video observations, such as the mass, restitution, velocity, and radius of each object, and friction of the scene. Then, given an input question, like what would happen next, and the choice, the green cylinder collides with the cube. We use a neurosymbolic parser to parse the question and choice into executable programs. In this example, the first program is a predictive simulation. We use our learned physics model to perform the simulation to get future trajectories. The second program filters the green cylinder object. And the third filters the cube. And then filter collision. We can see that the green cylinder collides with the cube, so the answer is true. With our differentiable physics model, the performance of the neurosymbolic framework (NSDR) is improved significantly, especially for the predictive and counterfactual questions, which require more dynamic predictions. Now we have shown the effectiveness of our physics model and the neurosymbolic program executor. However, the object concepts that we used as priors for our physics model are always difficult to obtain in real world, including the visual object concepts and language concepts. To design a more general and robust framework, we propose to jointly learn visual concepts and physics in our framework. Now let's see, how do we learn concepts for our physics model? Given raw videos and questions as input, we first extract the object-centric visual features from the video, including object-level features and interactive features, between two objects. We then assign concept embeddings to each word, including static concepts, which can be learned from object features in a single frame, and dynamic concepts are learned from object features in multiple frames, and event concepts, which require interactive features in multiple video frames. Given those visual features and concept embeddings, we build a concept learner that can project the visual representation into concept embedding space and performs nearest neighbor search to quantize the object concepts, which are then used as priors for the physics model. Therefore, our unified framework can jointly learn visual concepts and infer physics models from video and language by three seamlessly integrated parts, including a visual perception module, a concept learner, and a physics model. Take this counterfactual question as an example. Without the green sphere, what would happen? The corresponding programs are shown below. There are four objects in the video, and we have the object-centric features by visual perception module. The first symbolic program is to filter the green sphere. By comparing the object features in the color concept space with our concept learner, we know the object 2 is the green sphere. In the second step, we perform the counterfactual simulation by removing the object 2 and recalculate the object and interactive features. Next, filter green cylinder. The object 3 has the largest probability from the concept learner. And then filter sign objects. We get that it's the object 1. The last program is to filter the collision event. We project the interactive features between the object 1 and 3 into the event concept space to compare it with the collision event embedding. It shows a probability of 0.9, so the answer is true. Okay, let's move to the experiment part. Our experiment suggests that our model achieves high accuracy on Clever, especially on the predictive and counterfactual cases. Furthermore, by using explicit physical rules, our model requires less data for training. It always achieves better accuracy with fewer questions than previous works. It can also generalize to new concepts, such as heavier. Our model performs counterfactual simulation by assigning a heavier mass to the cylinder and answer the question correctly. The comparative results in the right table demonstrate the good generalization ability of our work. Here we show some examples. For the descriptive and explanatory questions, the answer can be directly get from our physics simulation. For the predictive question, we perform predictive simulation and we can get that the cube and the blue sphere collide. We then perform counterfactual simulation by removing the cylinder object and get the answer that the cube and the metal sphere will collide, so the answer is true. Our model can also be extended to real-world videos. In this video, the learned physics model performs predictive simulation and answers the question. In summary, we propose a reasoning framework with differentiable physics by combining three seamlessly integrated modules, including a visual perception module, a concept learner, and a physics model. Our framework has high accuracy, transparency, and data efficiency. The code is available. Thank you.